All right, people, these are the answers to single loop circuits and power. Power is like the wattage, the brightness of the light bulbs. It's joules per second. It is how quickly energy is being used up. All right. So like if you crank up the volume in your stereo, you're giving it more watts, more power. Okay. So Kaylin has two 10-volt batteries that each have a certain amount of joules of energy. So on this worksheet, I decided to give you the physics and chemistry unit of energy, joules, instead of the real world amp hours. Okay, so she wires one of the batteries to a 17 ohm light bulb, calculate the current. So your go-to equation for current is Ohm's law. I equals V over R, if you know everything. But if you go look at your diagram, you do know everything. Okay, and the voltage is 10 volts, and the resistance is 17 ohms. So there is 0.588 amps going through that circuit. All right, so again, just to remember what everything is, because there's a lot of hidden units, that means there's, I'm just going to round up to 0.6 for explaining, that means there's 0.6 coulombs per second going through that battery. And that battery is pre-committed to giving away 10 joules per coulomb. So you can see, looking at the two of these together, if you multiply the two of them, the coulombs are going to cancel and you get joules per second, which is how quickly the energy is being given away by the battery and being turned into light by the light bulb. Okay, so the formula for power is I times V. Because, again, if we look at the units, we have 0.588 coulombs per second. That's how quickly people are trick-or-treating, and the house is giving away 10 joules of energy for every trick-or-treater. So if you multiply these two together, you get 5.88 joules per second, or about 6 watts. Okay. Yay. That's how quickly the battery's giving away energy, and because energy is conserved, that's how quickly the light bulb is turning that into light. Okay, now we want to determine how long the battery lasts. So I know this is a little bit annoying, but there's two ways to calculate the time something's going to last. One is using the fake battery energy equals IT, if you know amp hours. We don't know amp hours, we know joules. So the other more like pure physics formula is definition of power. So this is why we did the cookie analogy in the beginning of this unit. The rate at which the cafeteria is giving out cookies is energy over time. And I'm using time lowercase because there's a hidden seconds. It's not hours. So I'm using capital T for hours, hopefully being consistent, and lowercase t for time in seconds. Okay. So the power of the battery is giving away 5.88 joules every second that the circuit is on. And we have 2.16 times 10 to the 5th joules. We haven't done energy yet. A joule is a tiny, tiny, tiny unit. It's basically the energy it would take to bench press a quarter pounder. So think about lifting a hamburger, and I have short arms, so I would need to lift it twice. That's 1 joule. That's a tiny amount of energy. Like a 100-watt light bulb is giving you 100 joules of energy every second. Okay, so it is not the best unit, and we are solving for time. Okay, so now we're going to cross multiply. So you get 5.88 lowercase t equals 2.16 times 10 to the 5th joules. Divide both sides by 5.88. And you get the time is 36,735 seconds. So again, not the best unit. I have no idea what that is. So we're going to practice our converting. 36,735. Sorry, this is a little bit in the way. Seconds over 1 if you like, and there's 3,600 seconds in 1 hour, so it will last 10.2 hours. So that, you know, we have a sense of what that is. We don't have a sense of what that is. Okay, awesome. Let's do number 2. She then hooks up both batteries, so that's like getting a 20-volt battery. So she has twice the voltage and she has twice the energy. So let's see what happens here. Clearly maybe something you don't expect, which is why I'm having you do it. So the first thing we're going to do is find the current. Hopefully that feels pretty plug and chug to you right now with meaning. We got 20 volts now over 17 ohms. So we have 1.18 amps. Clearly just twice the current. So if on a test you had said I've got twice the voltage, nothing else changed, I'm just going to double the current and you were explaining why you did it, that would be legit. But also just easy enough to do it. Okay, so now we have more current. We have 1.18 coulombs per second going through the cafeteria or going trick-or-treating. But guess what? Now, before their curfew, they're going to get to trick-or-treat at 2 houses. So they're going to get 10, every coulomb's going to get 10 joules from the first battery. And oh, psych, another 10 joules from the second battery. So not only are there twice as many of them, but they're going to 2 houses. So they're getting twice, they're getting some energy at the first house and they're getting some energy at the second house. So that's going to come into play for the logic question down in F. Okay, so now we're going to figure out how quickly the combined batteries are giving away energy. So the battery power formula, we're going to learn the power for appliances using energy, which not surprisingly is going to have to do with deal with resistance. The rate at which the battery is giving away energy clearly has to do with how generous the battery is, which is voltage. Okay, so your current is 10 joules per coulomb going by around and around and around, and they're going to go trick-or-treating twice. So they're going to get 20 joules when they for each loop. Oops. My current is 1.18 amps. I have no idea what I was doing there. 1.18 amps, 1.18 coulombs per second times that many joules per coulomb. The coulombs cancel and you get 23.53 joules per second or 23.53 watts. Okay, so now comes the interesting, cool, deep thinking aha moment. We're going to divide the power in circuit number 2 by the power in circuit number 1, and we get 4 times. So even though the current only doubled, because you're going trick-or-treating at 2 houses instead of 1 house, the power is, you're using up energy 4 times as much because you've got 2 factors of 2. I got twice as many trick-or-treaters and I'm going to twice as many houses to get candy. So I have 4 times the energy. So that light bulb is not going to be twice as bright. It's going to be 4 times brighter. But it also means I am using up energy 4 times as quickly. So the battery is going to run down quicker. So we're going to figure out how long the battery lasts. Definition of power is energy over time with a lowercase t for seconds. And we have 23.53 joules per second. I do have twice as much energy, right? Because I have 2 batteries and each battery has some energy stored. And we're going to solve that for time. So again, we're going to cross multiply and you get 23.53 T equals 4.32 times 10 to the 5 joules times 1. Divide both sides by 23.53. And you get a time of 18,360 seconds and I'm not going to show the conversion table just in the interest of time, but we're going to divide by 3,600 seconds, just like we did before, like on a test, show your work, that the units cancel, like that, equals 5.10. So it's only going to last 5 hours, even though you have twice as many batteries, so it's actually going to run down sooner because you are using up energy. You only have twice the batteries and you're using up energy 4 times as fast. So this increases the rate at which you're using energy more than it increases the energy that you have. That was the point of that. All right, moving on. Isabella has a 30-volt battery with a certain amount of real energy. She is designing a street light that she wants to last for 8 hours of darkness. Okay, question 8. Determine the current through the battery that would run the battery down in 8 hours. Okay, so we're looking for I, and I is pretty much in everything, right? Because it is all about me. So what do you know? You don't... Your 2 formulas that involve current, let's see, power equals I times V. And that is, what do we know? Let's write down, let's figure out what we know. We know the 30 volts, so that's good. We're looking for current, so that's good, but we don't know the power. So this, if you start to set something up and you realize you don't know something, again, we've done this enough. Hopefully you're feeling like a flexible problem solver. You're like, don't erase it. It just means you need to go to another column. And we don't have formal columns in this unit, but that just means let's try another formula. So we have it. This is energy. So we know energy, we know time. Let's start with the formula for power equals energy over time. Okay, so the first thing we need to do is say, oops, 8 hours is the wrong units. So 8 hours, and 1 hour is 3,600 seconds. So that is 28,800 seconds. Okay. And then power is energy over time. So let's calculate the power. We have 1.836 times 10 to the 5th joules of energy, and we want it to last for 28,800 seconds. So that is, sorry, on my PDF answers, I think I combined some formulas, but okay, so that is 6.375 watts. So it's a pretty dim street light, but that's okay. It is what it is. All right, so that's the rate at which the street light is using energy. Now we're ready to use the other formula, power equals IV. 6.375 equals I times 30 volts, and I equals 0.2125 amps. Okay. So that was a 2-step problem, actually 3 steps if you count converting. On the PDF answers, I merged the equations together algebraically before I plug things in. So whichever you prefer. All right, let's move on to B. Determine the resistance of the circuit that results. So basically, what's the resistance of the light bulb she's going to go get out of the physics lab? So now we know the current and we know the voltage. So now this is a simple Ohm's law, the fundamental formula, like F equals ma. We know the current is 0.2125 amps equals 30 volts over R, and we don't know R. So we're going to cross multiply 0.2125 R equals 30 volts. And then divide both sides by 0.2125. And you get R equals 141 ohms. All right, and then question C says determine the wattage of the light bulb. Based on the way I solved it here, we actually know that the wattage of the light bulb is, and I'm not sure if this I squared R, you might not have the formula yet. I think I might have broken up the power generated by the battery and the power used up by the light bulbs separately. So if we haven't talked about this formula this year, just know that we are going to get it. But you can also use the wattage of the light bulb is the same as how quickly the battery is using energy, right? Energy is conserved. So the light bulb is giving away 6.4 joules per second. Therefore, the light bulb is using 6.4 joules per second because the battery gives energy to the electrons, and then the light bulb takes it away and turns into light. But so I'm just giving you a heads up. Spoiler alert, this is the next formula we're going to learn. So we're going to take the current, square it, and multiply it by the resistance. And you get 6.37 watts, which again, we had already figured out up here. All right, number 3. Miss Groppy is building her own surround sound speaker. And so she can relax on her porch. And the resistance is 36 ohms, and she needs, I actually wrote this before I had my hearing aids, she needs the speaker to be 95 watts in order to be able to hear. Determine the current she needs to supply to the speaker in order for it to provide 95 watts. All right, so we want the current that she needs to supply in order to provide 95 watts. So since we care about if we care about how quickly the battery is giving away energy, we're going to use power equals IV because V is about the battery. If we care about how quickly an individual appliance is using energy, we're going to use power equals I squared R because that's how quickly this is converting that energy. So we're going to start with power equals I squared R. We want the speaker to be 95 watts. And that's going to be the current that we don't know squared times 36 ohms. Divide both sides by 36. And you get that the current squared is 2.64. And then you take the square root of both sides and you get 1.62 amps. All right, so I need 1.62 amps. So let's figure out how much voltage I need. Fundamental formula is I equals V over R. We know that I is 1.62. We don't know what the voltage is, and the resistance is 36 ohms. Multiply both sides by 36, and you get voltage is 36 times 1.62, or a 58.5 volt battery. All right, last question. I'm going to listen to 4 hours of music, radio, podcast per day. Determine the total amount of joules of energy used each day. So since power equals energy over time, you can think about energy equals power times time. It's like distance equals rate times time because power is a rate. Power is in joules per second. So if we multiply that by time in seconds, we're going to get the energy in joules. Okay, so again, this is one of those situations where it's really nice to include the unit so you can see what is happening. 4 hours is 4 times 3600 seconds. I'm not using a standard conversion chart because it doesn't say convert and show your work, but hopefully that makes sense. And you get 1,368,000 joules of energy every day. Again, a joule is a tiny, tiny amount of energy. That's why when they talk about building power plants, they talk about a megawatt power plant, because that's just the energy per day for a radio, right? And think about all the energy to heat and cool the home and all that kind of stuff. You're talking about, it's just a huge, it's a tiny unit. So it looks like a lot, but it's just because the unit is so small. All right. That hopefully everything's starting to build on each other. The Ohm's law is starting to feel like second nature, and you're practicing the new formula, which is power. So thank you for listening, and I will see you in class.